This talk is deep learning for developers, which is actually kind of a crazy. It's crazy to speak about this topic to people that don't have a formal machine learning background, because this is a very advanced topic, or it can be. A lot of data scientists don't really appreciate it or even know how to use it effectively. So before we just jump into code, I think it is helpful to cover some high-level background, 30,000-foot view, no math, and this will help you troubleshoot when you start playing with this, and we'll talk about why you would even use this. So before we get into the content about me, so when I'm not doing data science stuff, I try to get up into the cottonwoods as much as I can. I went today, I go every couple days. So if anyone in the room likes touring, talk to me afterwards, always going. A lot of people ask me what my background was, so this is a one-slide background. What my background was to get into data science. So when I went through school, there was no program called data science. There's programs now. So BYU has a capstone course in data science, and I think the University of Utah teaches several data science programs. But when the data science term started coming up, there was no traditional background. So what you see is most of the people who've been data scientists as long as I have, they come from really just all over the map for background. So astrophysicists, I'm chemical engineering, regular engineering, computer science, statisticians, they kind of come from everywhere. So I studied chemical engineering, worked for the Desert Research Institute, got paid by NASA for a short term doing website development for the space grant, so not as cool as it could have been. And then I worked for Intel and Micron for 5 years, and I went and worked for a hedge fund, and now I work for HireVue, which is an HR company, which I think is kind of hilarious, because if any of you guys think about HR, so at Intel and Micron, HR, that was for the adults that didn't know how to behave like adults. So that's kind of like they go interact with HR and they're in trouble because they threw a tantrum or they said something inappropriate. So I had a really negative taste in my mouth about HR. So when somebody told me about this startup and they said it was an HR startup, my initial reaction was probably what most of your reaction would be, is like, no thanks, I'll look elsewhere. But we saw, when I saw what they were doing, okay, so that's my background and that's what I'm working on right now. So these are some key questions I want you guys to be able to answer after sitting through this presentation. So what is deep learning? I want you to be able to answer that and think about it. A lot of people think of it as just, well, it's just neural networks. But something different happened in 2006, 2007, because if you were using neural networks before 2006, there's a good chance you haven't taken advantage of what these can do now. When is deep learning appropriate? So it's not always appropriate. So deep learning is a railgun, and sometimes you can solve your problem with a pistol. So don't bring a railgun when you can solve it with a pistol. And sometimes it won't even work. So if you're doing like categorical data in Excel, you want to build a prediction. And even when you're dealing with text, like with sentiment, someone from Newbie was here, if you're trying to predict sentiment, that can be hit and miss. It kind of depends on the length of the strings that or the sentences you're dealing with. Who services deep learning? So I encourage all of you guys to play with it, and hopefully we can give you the tools today to go play with it. But there's also people out there that'll just service it for you. So if you just want to start hitting an API and give them your data, they'll do it for you. And then we'll talk about some classic data types for deep learning. So, and I'm going to try to get through this real quickly so we can focus on the code. So I think the history behind deep learning is really, it's really entertaining to read and to think about. So this guy here, he works for Google now. His name is Hinton. And then this is LeCun. He works for Facebook. And these, out of the deep learning neural net experts in the world, these two are the most famous. And I think eventually we'll put this guy on a pedestal like Einstein, because these are his publications. He's been involved with deep learning since '76, and he's actually survived what they call 2 neural net winters. And so I don't know if anyone has talked to like their advisor at school or other people like, hey, should I use a neural network for this? And there's some negative sentiment on neural networks, like, no, don't use a neural network, use random forest, or neural networks will overfit. You know, what's happened is when Hinton went to school, there was a lot of negative sentiment around neural nets. When they were first suggested, people were writing books about how neural nets will be able to read, They'll be able to understand language. They'll be able to think like a human. Like people are really extrapolating what they'd be able to do. They'll be able to do voice to text. And some of that has come true, but what people found is they didn't generalize very well. They're really expensive to train. And so they lost a lot of the hype. And then Hinton invented something called backpropagation. And even if you're not involved with machine learning, you've probably heard of backpropagation. And so backpropagation allowed them to solve these nets in a much more efficient manner. And that kind of broke out of this winter. There was new excitement. People would see these white papers on, oh, look what someone did with deep learning, or not deep learning, look what someone did with neural nets, and then they try to apply it to their own research and it wouldn't work. And so they slipped back into this neural net winter. And this one was so bad that I was reading somewhere around the turn of the century, in the entire world there were less than a dozen neural net experts. So these are people like professors, full-time, they're getting funding, they're focused on neural nets. So all the interest around neural nets was almost going extinct, and luckily Hinton's group was getting funding from the Canadian government, and you can see from his publications he's very persistent. He's not going to give up on neural nets. And then LeCun made a breakthrough around 99. No one outside of the neural net community really cared. He made a big breakthrough with imaging, and then Hinton is credited for combining the two with his deep learning method around 2006, 2007. And really, people weren't that interested. Like, no, industry wasn't adopting it. And it wasn't until right around 2012 that Hinton's group won this competition called ImageNet. It's actually a really hard competition. So the competition is, I'm going to give you 1.4 million images. There's 1,000 different categories. Cat, dog, baby, woman, shark, like tiger shark, like very specific stuff. You have to write a program that will predict what image you're looking at. And a lot of universities would try to do this. And usually if you're doing a race, so if we have a programming competition for prediction for people in this room or the community, you have first place and second place and third place. The people that finish, they're kind of clustered together. And what Hinton did is he cut the errors in half. So he did so much better than the next person that it became international news. And then Google was suddenly very, very interested. They were already interested before, but I think within the year, Google did one of the largest acqui-hires in history, DeepMind, 400 million for about 20 to 30 hires, and they had no product. So Google just did a talent grab because they needed deep learning, and then Facebook, they started doing similar things. And now Facebook uses it for their facial recognition, so you probably noticed that your wife is being auto-tagged in an image. You didn't say that she was in the image. You might be disappointed by the results, but they're actually really good. They're supposed to be superhuman right now. And then Google, and then Microsoft is also a really big player in deep learning now too. And this has changed a lot of things. This is that ImageNet competition I was telling you about. So right around 2012, the second place was up here, and Hinton's group dropped the error all the way down here. And you can see since 2012, this is all using deep learning methods. So these are different improvements. And the thing that's the most exciting is in 2014, 2015, we surpassed a human's ability to classify images. So that competition, if I give you the million images and I say, go study all week, you're going to look at a picture of a tiger shark, you're going to look at a picture of a baby, and you're going to study, and then you're going to try to look, you're going to look at the training set or the test set, and you're going to guess what you're looking at. A human will have a 5% error rate because some of these images they're strange things. They're kind of hard to see. It's not always obvious. There's examples online if you look for ImageNet, human inaccuracy or something. You might be able to find some examples of this. So we've kind of reached a new era where in 2015 going forward, there's almost the expectation now, if you are doing deep learning, your product or your solution, there's a really good chance it'll be superhuman. And we're seeing that everywhere. It's not just with ImageNet. We're seeing it with all types of problems except voice to text. So we all have Siri on our phones and we're all disappointed. Like if I talk to Siri right now and tell it to do something, it'll let's just do a quick demo.
Ask him to read well-done poetry.
Oh, yeah. Let's see. I need directions to Walmart.
Peter Allen, home or Maine?
So it's trying to call someone named Peter Allen. Like, really disappointing, right? So, and there's reasons voice to text isn't better, but we have made some really big improvements with deep learning to improve it, and I think eventually we will reach superhuman accuracy on voice to text. Maybe not during the next 5 years, maybe not even this decade, but 2 or 3 decades from now, yes, voice to text will be superhuman.
Is part of that just because of that it's constrained by what your phone can do, or is it really sitting that up to some data center somewhere and still failing that bad?
So we use voice to text, so we've thought about this. You have certain, I think half of it is it's a problem. It's the problem type that's the problem. So if you look into the voice to text community, the researchers, most of them, they've been out of school for a decade. They have a very classical approach, and so they haven't really pivoted. And the other problem too, these training sets are proprietary. So if you decide you want to go train an English voice to text problem, sure, you can get some open source corpus. It's not very big. It's going to be crap. If you want to get a big corpus, like 10,000 hours, you're going to have to pay $3,000 up to $20,000, and you're not going to do that unless, where these other problems, like with the image stuff, that's all in the public domain. If I want to go download ImageNet, 1.4 million images, it's like 138 gigabytes. I can go download that. I have downloaded it, so I can download it. No one's stopping me from doing that. But the voice-to-text stuff, I don't think you have as many people playing in there, and you don't have really good open source libraries. So the best open source library right now for voice-to-text is something called Caldi, and it is ugly. It's written by a PhD student. It's a bunch of Perl and Bash and blah, it's just a monster. And people have consultants that the open source code is so complicated to run. A lot of people will hire a consultant, even though you downloaded it and you look through hundreds or thousands of these little files. A lot of times you'll hire a consultant to come make it work for you. Okay. So these next few slides, I put this picture here because this is a heavy topic, but it's an important topic to just hit on quickly. So this is a key part of deep learning. There's something called a convolution. A lot of data scientists I talk to, they don't know what a convolution is because they haven't needed to use a convolution. And to give you some quick background, this is stock data. And so this is Forex. Forex is going up. Let's say this is US, Euro, and you want to make a lot of money. And so you've got all your money in Euro, and you're trying to detect when it's going down so you can put it back in US, and then you can put it back in Euro when it's going up. And so people will day trade this stuff. And a very popular signal is this moving average. So I've got a slow moving average and I've got a fast moving average. And you see when they intersect, that's actually kind of interesting. So when this fast moving average dips below the slow moving average, that might be a sign of there's some momentum or there's something happening, and that could be my trade signal. So we could write a Python program right now that starts plotting this, and it decides to buy and to sell. And so this is a very classical indicator. It's called the MACD. But the important thing here is if I task you, use whatever language you want, you need to go write a program that will give me the moving average. If you do a for loop, like let's say I have a moving window, take the last 20 points, I'm going to add them up and divide by the 20 and get my moving average. That'll be really slow compared to matrix math, right? Like matrix math is really fast. You've got BLAS and LPACK libraries, heavily optimized. They'll beat that approach. But convolutions beat the matrix approach. And so convolutions, that's as fast as you can go when it comes to doing stuff like this. You can't beat a convolution. Convolution will give me the moving averages faster than anything else. And so with convolutions, there's this idea of a kernel. So these are kernels. And so for a simple moving average, I have identical numbers. And I'd actually have to divide by the count. So I've got, if I have a kernel that's 10 long and I have 0.1, it's sliding across this data and it's performing this operation. That gives me a simple moving average. If I want to do an exponentially weighted moving average, which is important in finance, that means I'm reacting more rapidly to the data that just happened. I want this to react very quickly to what's coming in. I would do this with my kernel. But these kernels can also do some very bizarre things. So something that's common in stock is this idea of a head and shoulders signal. And yeah, you can actually see it right here. So if my stock is oscillating up, I'm going to keep watching cartoons. I'm not going to do anything. But if I see a shoulder, a head, and then another shoulder, so if the oscillation is lower than the peak, that's called the head and shoulders, that could be a signal that there's a regime change, something's happening, I'm going to short the stock. And so this head and shoulder signal is kind of complicated because what if my head is really wide? What if my shoulders are tiny? Like there's a lot of variation, right, that can happen. And so I can actually do a kernel that will activate. So when it sees a head and shoulders, it's going to produce a very large value. And so my program can find it. And this is, and we could like iterate on the board and you could play with it. You could just do like random numbers through here and see if you can find something that flags on the head and shoulders signal. Or you could actually design it. You could kind of look at this and, well, I think for head and shoulders, I want to give a lot of weight to the center. I want to do this. You could come up with these. With deep learning, these kernels are solved for. You don't think about it. So the human is not on the board thinking about this head and shoulders signal. You just give the deep learner, these are head and shoulders, and these are not. And the deep learner can figure out this kernel. And so if that wasn't complicated enough, for images, we actually have 2D kernels. And so this kernel is sliding across the image, and it's actually doing a mathematical operation on the pixels. And so you can do a ton of stuff with these kernels. I can sharpen the image, I can blur the image. If I want edge detection to really make my edges pop. So how many people here do image processing? Does anyone? Okay. Image processing is a ton of fun because you see what you're doing, right? Like you load in an image, you do some blurring, some sharpening, you have a lot of eye candy. So convolutions are popular for a lot of the programs you guys use on the back end. And this is key when it comes to prediction. So these 9 numbers, this is what the deep net is solving for, these convolutions. And that's called a feature. We're almost done with this. So I also need to give you background on what a neural net is. So this is the simplest neural net that I can come up with. So I've got 3 inputs. They're going to be added together, and they're going to continue on. And so let's say I'm trying to predict if I should give you a job. So the first input is your GPA. Your GPA is coming in. The second input is how many patents you have. It's kind of a dumb example. And then the third issue is how many LinkedIn connections you have. Also stupid. So I have these things coming in, and I want to predict yes or no. Do you continue on or do you stop? And I have these 3 weights. I don't know what the weights are. So maybe GPA is really important. Maybe the number of LinkedIn connections are important. I don't really know. I want to solve for these weights. And so another thing that can happen is I can have hidden layers. And so this allows me to have some pretty strange effects going on where I could have the GPAs being combined with LinkedIn connections, and I'm getting this nonlinear effect. And when you look at this looks complicated, but to kind of set the context, with ImageNet, you can solve models. If you're motivated this week, you can go solve an ImageNet model. And that model will have over 100 million connections, 100 million unknowns. So look at this. This seems complicated. Imagine 100 million weights that you're solving for to predict something. And Google, they announced that they have models that are in the billion status. So they have 1 billion unknowns that they're solving for. And the brain has 1 trillion connections. So if Google's talking about 1 billion now, 10 years from now, someone's going to be talking about 1 trillion. And so the idea of building a deep net that has more neural connections than any of our brains 10 years from now, that's not as crazy as it might have been 10 years ago. So that's kind of, so Skynet is coming.
So in those, in the current, kind of state-of-the-art neural networks, how many hidden layers are there?
I think some of the best ones will have, I think, over 1,000. They'll have like 1,000, which is kind of nuts. So Baidu, they have their, or Microsoft came out with a new method. VGG, which is a very popular deep net design, it has 19, like 16 to 19. But the 16 to 19 different layers or feature sizes, that can still back out to hundreds of millions of connections, or not hundreds of millions of unknowns.
The most recent, like ImageNet, when there was like 150 or something like that.
Oh, and was that Microsoft?
Yeah.
Okay, yeah. So the Microsoft model on this. So there was a paper out there. If you search Microsoft 2015 DeepNet, the one that won was the 100 layer, but they tested 1,000 layer just to show that they could do it, and they saw that the gain wasn't worth, like it was just a lot of times you're fighting in this diminishing return area, but I don't know, like we're below 4% now on ImageNet error. So 2012 we were at 15%. Now we're below 4%. 5 years from now, are we going to be below 1%? Like, no one really kind of knows where.
Because humans can't judge whether or not that's correct. If it's better than humans.
Oh, well they.
You probably write a program to predict that.
Yeah.
Predict what the prediction rate is.
Yeah, extrapolate it out.
The curve was
So-
pretty obvious.
So the other thing you have to understand with neural networks is there's this idea of an activation, just like our biological neurons. So if something's poking me in the foot, I don't really care. But when you take a knife and shove it in my foot, now it's gonna exceed some threshold. I'm gonna do something. And so in the neural net, we've got these stimuli that are coming down, but nothing's happening. And then when you exceed a threshold, it's going to continue to signal on. And just like that, neural networks also have activation. So if you've ever seen a classical neural network, you've probably seen something like this, where with deep nets, the most popular is this RELU, and I'll explain what that's doing. It's actually, it's really trivial. So all this is saying is if I get a value upstream coming to me, if it's negative, I'm going to ignore it. If it's positive, I'll allow the value to continue. So I'm not even doing anything I'm not performing an operation to the data. These other lines, they're performing a mathematical operation, where this is just, you're negative, you don't activate, you're positive, you continue on. So if I'm doing, if I want to predict so if I'm looking for like a dog or a cat, and the cat eye is very distinct, right? So I could predict if I'm looking at a cat just based on the eye. So that might be a very interesting feature. It's coming down. I'm seeing some of the fur. It's not activating. I see a cat eye. It's going to activate. It's going to be positive. It'll continue downstream. Okay, so feature ensembles. So think about what you guys are doing right now with your own neural nets in your mind. You're able to see that John Lennon, right? And Harry Potter. So you see the similarity. I didn't have to tell you that they look similar. You just see, oh yeah, they do look kind of similar. And so think about what your brain is doing. So you're seeing the circular glasses, so that's one feature. You're seeing, the mouth is kind of closed, it's serious, that's another feature. The shaggy hair, that's another feature. Maybe their noses, or the fact that they're looking forward, they're not looking to the side. So it's kind of the exact same pose. And what you just did is you did what we would call a feature ensemble. So the shaggy hair, that's kind of a macro feature. That's really big. The glasses, maybe you're looking at, kind of the center of the glass. That could be a smaller micro feature. So you took this really complicated ensemble and you made you made the connection that they're very similar. And then same with this dog. They've got, look at the bags under the eyes, right? They're kind of similar, and then they've got the hair. And then this is a picture of Obama on a piece of toast. And to kind of drive this even further, suppose I take 6 bites out of this toast, and I hold it up and say, hey, isn't this funny? It's a picture of Obama. you're not going to see it because you're missing out on this feature ensemble, right? Like you need to see his ear here. You need to see his eyes. If I take a couple bites, you can't you can't make the connection anymore. And just like what your human brain did, the deep net will do the exact same thing. It's going to create a feature ensemble. So those convolutions, it's going to solve for a lot of different convolutions that activate on interesting features like a cat's eye or some fur. And it will also do, they call them deep nets because it'll do multiple feature levels. So it'll solve for macro features and micro features. So this is an example. So it's probably really hard to see. So one kernel, so these kernels are these 2D convolutions. And the most popular now, people just do a 3x3, but when they started with image nets, they do a 5x5 and a 7x7. They do much bigger convolutions that would give you a lot of flexibility. Like you could do a 20x20. It's a bad idea, but you could do that, and that would be something very obvious. Like so here I've got a nose. I've got the inside piece of the glass, and then I can't even see my own slide. So whatever that was. Oh, it's some hair or something. So on the very first layer of the deep net, we're looking at micro features because we have our little 3x3 or 5x5 convolution. We're looking for something at that scale that will activate. And here I'm telling it we have 3 features. These 3 features are unknown. We're not telling the deep net that we like the glasses or that we like the mouth. We just say we think we have 3 features. They're initialized with just total random junk. And then that's where the deep net will iterate over and over and over. And these things will start to converge and and they'll resemble a real feature. And then on the next layer, we do something called max pooling. And all that's doing is it's taking, the most popular one is I take 4 pixels coming in. So these convolutions actually each create their whole new image. So this convolution is run across the entire image, and it produces a new image that might look really funky, where the corners would be bright white, and then everything else is kind of gray. You can kind of recognize the image. But what it's doing is these things are activating. So these images that come in, on the very next layer, we do something called max pooling, where what it does is it looks at a 4x4 square of pixels, and it looks at whatever the maximum value is, and allows that to continue, but ignores everything else. And by doing that, your image size is reduced down to 25% of what it was before. And then you repeat the process with new filters. And by doing that over and over again, when you get down to the bottom, now your image is very small, and now that 3x3 is actually picking up on some larger features like, oh, you've got a beard, you must be a man, something like that. And then I made this red because I wanted it to be clear that this is not the original image anymore. This is actually, because when you start going through the network, it becomes this very complex ensemble where the thing coming into the next layer is actually every single image from the previous layer. So this can become really ugly, but the nice thing is we have code that makes this really simple. And this is a visualization that shows you what's going on. So this deep net is predicting what the speed limit sign is in Europe, and it's actually able to classify, has all these different outputs, it's able to classify that this is a 60 kilometer per hour sign. So the input comes in, and I've got 4 different filters here, or convolutions. So this is the post-processed image after we passed our 5x5 convolution over it. So you see they kind of look the same. You can still tell it's the original image, but there's different lines that are activating. And then we downsample it, and we have our final layer where we do the classification. And now we're going to go look at some code. Yep. So finally, time to look at code. And then one quick thing. Oh, I think I only have three more slides left, so I'm going to finish this up, and then we'll actually run real examples. So this is some Keras code, and when it comes to Python, you have a lot of different libraries that'll do deep learning. You have Caffe, you have NoLearn, Lasagna, Theano, and a lot of people write wrappers. And I started with NoLearn, and I was really frustrated by it. because you have CUDA. Have you guys heard of CUDA? Do you guys know what CUDA is? So CUDA is a NVIDIA proprietary language that runs on the GPU, and NVIDIA was first to market to allow researchers to run code easily on the GPU. Now they have OpenCL, which is supposed to be a standard. And I guess the benefit with OpenCL is it will fail gracefully to the CPU. That used to be a big problem. When I worked at the hedge fund, if you had a collision or something in GPU memory, it would just totally bonk, and it'd throw these CUDA exceptions where OpenCL, if the GPU is not available, it will default. But the problem with being first to market is so many people have built out these fantastic tools. There's not a big driver to switch to OpenCL because CUDA is so nice. CUDA has all these fantastic tools. So Theano runs on top of CUDA, and then there's a Python wrapper called Lasagna that someone wrote that runs on top of Theano. And then someone wrote something called NoLearn that runs on top of Lasagna. And what they're trying to do is they're trying to take something that's really complicated and they're trying to hide it from you. So the higher up you go, and the problem that happens is your hands start to get tied. So when you get to NoLearn and something's not working, you don't have a lot of options. Where down at Theano, you have all the options. You can do whatever you want. Keras is a new one. It was written by someone at Google. Everyone I've talked to that plays with it, they really like it. It's one of their favorite libraries compared to other Python libraries out there. Here's an example where we actually built a deep learning model, and we're going to go into this in more detail and run one. But it's really not a lot of code to do something very complex, like what we saw before if you want to predict a cat or a dog. So when is deep learning appropriate? So something you have to keep in mind is if you're doing text classification like sentiment analysis, or you just want to predict, is this a bad image or something, you have these classical machine learning methods that are, in some cases, they're very, very fast. So this Bayesian method on your Twitter data will be incredibly fast. It's very lightweight. It's efficient in memory. You're probably going to get 80, 90% of the theoretical value just from that. Where deep learning, to train it, you need a GPU. To evaluate it, you don't need a GPU. Like if you want to have your phone evaluating some model, I'm going to take a picture of something, it'll tell me if it's a cat. I don't necessarily need a GPU for the evaluation, but I definitely need a GPU for the training. To teach it that this image is a cat, you need a GPU. And so you're looking at additional hardware and time to set this up, where this is something in Python, 2 lines of code, you could run this immediately, find 80, 90% of the value, and be done. So something to think about if you do want to play with deep learning in your projects. So who services deep learning? MetaMind, they're out of Stanford. They raised $8 million for their Series A. Clarify is out of New York. It was kind of funny because I reached out to the founder of Clarify to try to give him a job. I didn't know he was the founder of Clarify. I've actually pissed off a few people doing that. The CEO of Data Robot, I guess on LinkedIn it says he's a data scientist. I tried to recruit him, and he sent me a really mean email saying, like, if you had seen I went to Techstars, you wouldn't try to recruit me. But Clarify, they raised I heard back from the founder, and I was really excited, like, oh, maybe we can convince him to come to Utah. And then apparently he just raised $11 million, and he was trying to do a reverse sell on me. So that's why he got back with us, is he wanted us to buy his services. So these companies have really slick APIs. You can call them, and if you have images that you've already put together, but maybe you're having a hard time with the deep learning, it's not converging, you can package your images up and you can send them through the API, and a lot of them have like free API access, so you can at least see, oh, this is working. And that might be a good check, because these people know what they're doing. They have a lot of deep learning experience. If they can't find any predictive value with your data, then maybe you shouldn't invest the hours and the time to attempt to find value with your data. So I'd always recommend doing something quick, fail quickly. If you can fail really quickly, that's one way to do it. And then this group, they advertise that they do deep learning on everything, which is kind of a bad thing. Have you guys noticed that with vendors? Like, if they promise they can do anything, they can't really do anything. Like, it's a bad thing if they're not specialized. And then this is a local project I'm working on with a few people in the area. We do have an API that you can call. So it's still a work in process. These other ones on the top are much more advanced. They're ready to go. You can test them tonight. So let's look at our example. So, and before we look at, this is the very last slide of the presentation. So before we look at, if you can see a difference with your eye, the deep net, there's ways to help these deep nets. So this is some MRI data that I was playing with. So this is what the original MRI looks like, and you have to predict if this individual has a disease. So there's something that's very popular in deep learning called demeaning. You take the average of your data and you subtract it out of all your observations. And some of your observations might look really strange if you do that, like a picture of a cat. It's going to look really weird if you demean it. But what this example with the MRI, this is the exact same image. We've demeaned it. Do you see how this image really pops with information? Like certain areas in here that weren't that interesting before are now, there's a lot more variation in that area. So this will actually help the deep net. So this link, hopefully you can read it. It's bit.ly lambda L for Lambda Lounge. That will take you to a Git repo, and I have this notebook called Light, Deep Learning Tutorial Light, in Python, and you can run this on a CPU. You do have to have sklearn installed, NumPy, and Keras installed. I think you can pip install everything except for Keras. You need to clone that, or you need to get it from the Git repo. Maybe you can pip install it now. Oh, you did? Okay, great. The other thing I've noticed too, Keras is a very rapidly evolving library, which is kind of annoying because they've changed. Like examples that worked 6 months ago will now totally bonk and they won't work. And you see that a lot with the deep learning libraries. Especially with like NoLearn and Theano, they have so many improvements that are coming. Sometimes it's hard so it's important to be up to date on these libraries if you're playing with them, especially if you want to run examples. So the Hello World example for deep learning is this MNIST handwritten data set. And so these are just handwritten digits. So 0, 1, 2, 3, 4, 5, up to 9. And you have to predict what the handwritten digit is. And this is actually really interesting for optical character recognition. So if I give you a receipt, a really good app that someone should make is I want an app that I can take pictures with my phone, and it'll totally scrape out all the information in the receipt, and then it'll put that into Mint or my accounting software and tell me I spent too much on asparagus, like last month. So, and if you want to do that with handwritten data, that's a lot more challenging because people can have really, look at this writing, it's really sloppy. If I want the computer to automatically know what I wrote, that can be kind of a stretch. So this MNIST example, I can zoom in more. Can you guys see this okay? Right here. So this is Python code. So one of the most popular libraries for data science is this sklearn library. And one of the things I really like about it is they have this import data sets. So this MNIST data set, you can go download that directly from the university that created it, but you'd have to format it and you'd have to do different things to get it ready. Where I can just import data sets, and within my data sets I can tell it to go fetch this handwritten data set. And when it does that, it fetches it and it's already in a Python format ready to go. I didn't have to run a shell script or do different things to prep it. It's ready to go. I didn't have to go look anywhere. And so let's actually look at that and see what it looks like. So if I look here, so I've got, oops, I don't want that. So this X, so anytime with machine learning, when you have an X and Y, an X will always be your features. That's what you're putting in, and the Y will always be your output, what you're trying to predict. So this X data set, when you look at it, it's really confusing because this is supposed to be an image data set, but this is the format. So I'll explain what's going on. So I have 70,000 rows. I have 784 columns. What they've actually done is the image is a 28 by 28 black and white pixel image. So the original image just looks like this. So this would be a 1, and this would be a 0. So this is 28 pixels, 28 pixels. They flattened it, so this now becomes this big long row that is 784 columns, and the columns represent the pixel data. And then the rows represent the observations, and So we can look at the first row and see. So if I'm curious, what number is this on the first row? I can just say, so the first y is number 0. Let's see. Oh, so it's actually in order. So they have zeros, ones, so they're all grouped together in the data set, which can be a really bad thing. A lot of times you don't want them to be grouped together. And so these rows would correspond, like if this last row here is a 9, so that represents a 9, and that might, see this pixel data? So anyone that does image processing, you immediately recognize like, oh yeah, I know what I'm looking at now. So these are actual pixel values, and so 255 is white, the 0 is black. And so I can see that it's not just a Boolean image, they're actually giving me some gradient, like some gray, there's some grayness here, there's some black here, I've got some variation. And if I had, if this was showing right, you'd actually see that this was a 9, and that would be kind of fun, but you can't tell it's a 9 because it's kind of messed up on the rows and the columns. Okay, so now we know what that looks, now we know what the data set is that we're dealing with. So before you can use deep learning, you have to become familiar with this concept of a tensor. So how many people know what a tensor is, or if they've used them? So in normal machine learning, I would just run with this x and y. I'd throw it right into a random forest, some other method. I could care less that we flatten the image. I can build a predictive model and actually be pretty good. I'll probably get over 90% accuracy just doing that. But with deep learning, it's expecting this concept of a tensor. And so Python has these nice functions to reshape stuff. And so what this is saying is I want to take that data set and I want to reshape it into this format. So the same NumPy array, it was 2-dimensional, now it's actually 4-dimensional. So it represents 70,000 observations. The next one is color. So this tells me it's black and white. If there was a 3 here, I know there's an RGB component, or maybe you have some hyperspectral data and you have 15 components, or MRI, you've got 256 slices. And then the next one is my X and my Y. So I can see the 28 by 28 pixels. Another way to visualize this is imagine a stack of images. So I've got my 28 by 28 image. I've got a stack of 70,000. And now I can feed that into the deep net. So the deep net is expecting a tensor object. And that's true with Theano. I wonder if some of the higher ones might allow you to get away without doing a tensor object. I would assume they all want a tensor. Do you know, Ben? Okay.
The ones I have, the TensorFlow.
Yeah. TensorFlow wants a tensor as well? Yeah.
Different ordering.
Okay. Oh, and that can,
It's the name.
well, that, yeah, and that can really burn you too, the ordering. So once you understand deep learning, if you train a model in Cafe and you want to move it over to this JavaScript client, or you want to move it over, you can move models around. You don't have to, if I train a model in TensorFlow, I can go move it to Cafe. Some of these, they've written wrappers to help you. If they haven't, you can get burned by this ordering thing. Some of them are really weird, like the RGB values on a color image are switched. So that's something to be aware of if you're trying to port a model across. So we've created this tensor object, and one of the things you definitely want to do when you're doing any machine learning is the worst thing you can do is train on all of your data and look at your metrics. How accurate were we? We're 90% accurate or 100% accurate. You always want to carve out part of the data that you can't touch. In this, this is a huge problem for people in data science. They're always fighting this, and they're always getting burned by it. So here, I really like this thing called stratified k-fold, and this is actually pretty complicated. I'm sure it's the first time a lot of you guys have heard of this. So what this does, I could just randomly take the data and cut it. I've got 80% of, I'm starting at the beginning, I've got 80% of the data, I could just cut it and throw it and pull 20% out. The problem with that is, what if I end up holding out all of my 9s or all of my 8s? That'd be a disaster. Because if the deep net can't see any 8s, that's really going to hurt me. So what stratified k-folding does is when it splits it, it makes sure that the distributions in the training set are the exact same as the test, and that's really good. You always want that. You don't want to have them be radically different because that can you can see things you weren't expecting. And then the other thing I do, remember how it was ordered? Zeros and ones and twos. That's terrible because the deep net it's not going to converge if you're sent. You want to send every time you send stuff to deep net. You want a lot of variation. You want to show it. You don't want to send all zeros. You want to send, here's a 0 and a 1 and a 3 and a 9. And so here I shuffle it. And so now that I've split it and I've shuffled it, I have this X train, Y train, X test, Y test. So now I can train a deep net and I can test it. So now I'm ready to go. And then the very last thing that they made us do is they made us take that Y. So if you remember, Y is just a single vector that looks like this. It's kind of hard to see. It's really not that interesting because I have zeros and ones. Like if I just pick a random index like 1,000 to 2,000 or 1,020, still zeros. That's dumb. Ones. So I've got zeros and ones and twos that just go on and on. And one of the things I want to do is I want to shuffle it. So down here it shuffled these. And so now I've got this really nice mix of different classes that have been kept. And then one cool thing you can do is I can actually visualize these numbers. So here I just told it, I wanted it to loop through and just turn the first occurrence of these different numbers. So you can actually see what these numbers look like. So you can see they're kind of sloppy. Like look at that 8. The bottom of the 8 was almost so small it disappeared. And then this 4 is really good, but you'll see some 4s that look just like 9s. Like even from a human looking at it, you're like, they're almost touching up there, and it looks circular. So that's kind of cool. You can look at the data. So now we're actually going to do some deep learning. So with Keras, so do you see here how it says using GPU device? As soon as I load the library, it'll tell me it found the GPU. And this can be a headache if you're setting up an Amazon instance for the first time. I think I heard you mention that you found an AMI.
Yeah.
So there are AMI, pre-built AMIs on Amazon. If you go Google around, you can find one where all of this is configured correctly. You don't have to download the CUDA drivers. You don't have to set up the Theano config. It's ready to go. And so I'd recommend playing with that because you might get kind of frustrated initially. Because you'll go here and you'll run this line and you won't see the GPU flag, and then you'll have to go troubleshoot. And so there's usually always some troubleshooting initially.
On the car right here, I can verify I was trying to build an Amazon EC2 instance from scratch, installing CUDA, and it's pain in the ass. So if you have an AMI ID, just use that.
Yeah.
I also have a question. When you're calling stratified k-fold, why did you pass Untitled equals 7? Is that just what?
Oh yeah, sorry, I just glazed over that. That's really important. So this is something that confused me when I was getting into data science. So you'll hear some people say you train on 80%, you test on 20. You train on 70%, you test on 30. And you might ask, well, who's right? I've got 2 really smart people telling me train on 80. This guy's saying train on 70. And the thing I kind of realized is, well, they're actually both wrong for different reasons. And this is the dilemma that you have. Because if I really want to get the most accurate model ever, I'm going to train on 99% of the data. I'm going to have a 1% holdout. But the problem is, whatever performance metrics I get on that 1% holdout, it's not a big enough set. Like, what if I check my accuracy and it's 0%? Because I only had one value and I missed it. Well, that's not really fair. Or what if I check my one value and I get it right and I get 100%? So I have this issue where, yeah, I trained on 99% of the data. I have the most generalized model possible, but now my metric that I'm reporting on isn't big enough to be meaningful. And so the way people address this is if you go look up stratified k-fold, what that actually ends up doing is it would build, in that case, it'd build 100 different models. So it would take 99% of the data, it would test on one, and then it would take 99% of the data, including that one, and test on another 1%. So you can kind of imagine if I have this table and I cut it up into tenths, I'm going to build a model on this 9, test on the 1, build a model on, and what ends up happening is in the end, I end up testing on every single observation out of sample. So the performance metrics I tell you are way better than what that guy with the 20% would have told you, because I've got a huge set that I tested on. And my model will be more accurate than his because I trained on 90% of the data. So that's the right approach. But sometimes with deep learning, it's too expensive. So for this deep learning run, we'd have to run it for like 5 days to do a true like k-fold. We're not going to do that. So that's why you just pick a single cut.
So the 7 here means 7%.
The 7 here means we're going to have 7 cuts, which translates to like 85%. We're going to train at 85% and test on 15. Yeah, so the popular folds might be 10. Sometimes for faster machine learning methods, we'll do a lot more. We'll do like 50 or 100 because you get those gains on training on more data, helps you generalize more. So the first time you load this, it'll tell you have a GPU. The second time you load it, it doesn't tell you. But if I restarted the kernel, it would tell you that we have a GPU. So now, batch size. So this is a new. So the GPU is an interesting device. So this code is physically running on the GPU. It's not running on the CPU. My CPUs they're essentially being wasted. The GPUs aren't being utilized. This code runs on the GPU, and it's running in GPU memory. And one of the issues with that is the GPU doesn't have as much memory typically as the computer does. So you have 2 different memories. And so that's one thing that we have an issue with. We don't have enough memory on the GPU. I can't take the whole data set and shove it on the GPU. And then the other problem is, if I'm going through and testing all of these images, it's really dumb. So if I initialize my kernels with all this random noise, and it takes me 1 million images to get a score back to say I had a really bad initial guess, that's really stupid. Because that'll take me hours to go through all the images and give me back an error. So with deep learning, they have this concept of a micro batch or a mini batch. So this batch size will take 128 images, it'll throw it to the GPU, it'll do the testing, it'll get an error back. But what that allows me to do is it allows me to learn in real time. And you'll see this. So we won't even finish all the images, but our errors will they'll already be going up and up. They'll be getting better. So this mini batch, you can play with this. Sometimes you'll get a memory error in the GPU, and if you get a memory error, your initial thought is, well, I have to reduce my batch size. And so for some images with high resolution, you have to reduce it way down to like 6. So you're only sending 6 images to the GPU at once. Number of classes, we have 10 things we're predicting, 0 through 9. Number of epochs. So an epoch is when you go through the whole set once. So I've got 70,000 images. I'm going to go through the whole set once. I'm going to do it again and again and again. And that's what how the deep net's going to learn. The image dimensions, 28. Number of filters, so that says 32. So what that means, I'm allowing the deep net to find 32 convolutions of interesting features about my numbers. So imagine like the little 4 intersection, that could be a convolution. Maybe the 9. So that's a pretty big number, 32. And then I have the filters below. So you could try a smaller number like 16. The fewer number of filters you have, the faster your deep nets will work, but you're not going to get the same accuracies. And if you have too many, like let's say I just make my number of filters 128, my deep net won't converge. And this is a dilemma that anyone has dealing with. If you start playing with deep learning, I promise this will burn you. The first few weeks, you'll get really frustrated because your deep net won't converge, and you don't know why, and you don't know what to do. And this is where someone with more expertise can kind of come in, and we'll talk about why they don't converge. So this model object, I define it, and I'm at the very beginning, I'm doing 2D convolutions. They're going to be 32, 3 by 3, so I've got 9 values I'm going to solve for. Border mode valid, so you get really weird things that happen at the edge of the convolution, and you have different assumptions you can make. So I could do a border, a full border, where it has to be 28 by 28, or if I can do a valid, where this output will actually be a smaller image, so it's going to crop.
I don't know if that makes sense. So if I take if I take that 9 by 9 and I slide it across the image, at the edges, I'm not able to really calculate a convolution because I'd have to make some assumptions. I have to make an assumption that there's a 0 pixel that I can't see, and I'm not going to make that assumption. So convolutions, you tell it valid, full, you just tell it what you want. And so this will go through, and then that's our activation. Remember that RELU, negative you stop, positive you go on. That's that right there. And there's lots of different activation functions. I could just change that. So this is really nice code-wise. I can make one change. I've already done something very advanced. Like I've already changed my neural net model because I changed that to a different activation unit. And I don't have a PhD in neural nets, and I was able to just do something quickly and see if it improved my accuracy. And then this max pooling, that's where it's downsampling. We haven't talked about this. This is dropout. This might sound very strange. So the problem with neural nets is they are going to overfit like crazy. So if I'm solving 100 million unknowns, I can fit an elephant, right? Like, I can fit anything I want. And so,
What do you mean by fit?
So if I have a training set, so you give me, so for this example, we've got 70,000 images, zeros, ones, nines. The neural net could probably get 100% accuracy on the train, but then it's going to get worse than random on the test. And so one of the things you're always fighting with a neural net is how do you make sure it doesn't, what people call overfitting. Because you want it to, the way it performs on the training set, you want it to almost perform that well on new data. And so this dropout, what this is doing is it takes 25% of the things coming through and just randomly throws them away, which sounds like a disaster. But every time it goes through and learns, you're just randomly throwing stuff away, and that helps protect against overfitting. That's one way. And then we'll talk about another way in a minute. So coming through a neural net, you have this two-dimensional thing. Eventually, we have to flatten it. Eventually, at the very output has to be a decision. Yes or no, 1, 2, 3, 4, 5, 6, 7, 8, 9. Cat, dog. We have to make a decision at the end. And so we flatten it, and then at the very end, we're predicting how many classes we have. And then I have to define the optimizer, how it's actually going to solve it. And this optimizer is key. I can change it to something else, and it will solve much better. I can change it to something else, and it'll make it worse. So this library is really nice. I can quickly try a few optimizers. I can change my number of filters, number of epochs, my dropout rate, and I'll get a totally different accuracy. So I have ways that I can play with this. I may not know everything about deep learning, but I've got little knobs I can play with and see what happens to my accuracy. So we're going to run this. Awesome. I love it when it does that. Oh, there we go. Okay, it's actually running. So this little asterisk shows me it's running, it finished. So this is compiling the CUDA code that is now going to run on the GPU. So we don't want to program in CUDA. We want to program Python or Julia or some other like JavaScript. And when it gets pushed to the GPU, it's going to run. And now that we've compiled our model object, I can actually start training it. So I'm going to start this running. I'll tell you what it's doing. So these CUDA errors can be kind of tricky sometimes. Input shapes. Apologize for that. So when it's going through and solving, it's pushing everything to the GPU, but it's doing it in these little micro batches because we want to learn quickly. We don't want to wait for 70,000 images to find out that we had a really bad initial guess. We know we have a really bad initial guess because it's just random crap. So we want to find out immediately. Within a few, sending 128 images, we want to find out within a few micro batches that we need to make a change. We need to make an optimization. So now I'm going to compile again. So what this is going to do, okay, so I have no idea why it's working now, but it's working. So this is going through at batch size 128, and I really like this output. Like this is really nice output because it tells me what my ETA is. So if you're going to go to lunch, crap, I need to go to lunch, or I need to shut my laptop. I forgot to put it in a screen session. I've got my ETA, so in 4 seconds it's going to finish the epoch. It's showing me the count on the images that it's testing. And so it finished the first epoch. And so the optimizer doesn't really care about our definition of accuracy. The optimizer has its own loss function. It's driving the errors down, and we've defined the loss to be this categorical cross entropy. You could define it to be something else. So this is what the neural net is fighting to reduce. So the neural net has a solver, and it's trying to change these little kernels to improve this loss function. And then I've got two accuracies. So I've got the accuracy on the training set. So if this accuracy goes to 100%, and then the accuracy on my validation is like 10%, that doesn't really, like that's overfitting. I'm going to see I have a really good model on train, but it doesn't generalize at all. And so each of these is called an epoch, and this is running on the GPU. If this was running on the CPU, it'd be about 32 times slower, which is funny because sometimes that happens to you. You start running your deep net, and you're like, man, this is taking forever, and then you find out that you have an issue with your GPU, like something happened with your GPU drivers from an update, and it's not running on the GPU. So,
quick question: are you getting like a node per pixel as you're going through? Is that a sizing consideration you have to worry about, or do you even care about nodes in the network?
So distributed deep learning is surprisingly not as readily available as you'd want it to be. So if you want to be running deep learning on 10 different GPUs on Amazon, Keras will not support that right now. But there's TensorFlow, which has issues. It doesn't support the GPU drivers on Amazon. Like TensorFlow has issues. The best one right now for Amazon is called MXNet. So it's open source. You can do a clone on it. Once you understand what the deep net is doing, distributing it is not rocket science. Like for you to distribute Keras to 10 GPUs, if you know what you're doing, I imagine you should be able to do that in less than a week. Like that's not some mind-blowing task. But unfortunately, no one has done it yet. Because I would like that if someone else would do it. So this finished.
Ben, are you saying one problem for multiple GPUs?
Yeah. So you're talking about one problem to multiple GPUs? Oh. Maybe.
Give me more information than I was.
Oh, okay.
I was going in this direction. You gave me something much more interesting.
Okay. So we're training a 28 by 28 pixel image. Let's say this is a 512 by 512 pixel image, and we have 1 million of these. This type of approach will take a month or two on a GPU. Like you're already running on a GPU, but it's going to take a month. And most of us at work don't have a month. And especially if you're servicing a customer. Like, can you imagine if I'm servicing a customer? Your model will be ready in 1 month. Like, no. And the dumb thing about the cloud is you're paying the exact same price if it takes a month or if it takes 1 hour if you can distribute it. And so we obviously want to distribute it. Fire up those instances and shut them off. So let's look at what actually happened. So you can see our loss started out pretty high, 13, went all the way down to 3. So we had great improvement on loss on train. And then when we look, this is our secret validation set. We're passing it in just so we can watch what's happening. But this is not being used for any learning on the deep net. So my validation, I actually got up to 84% accuracy on my validation set. If we let this keep going, it gets up to like 99.2, or it does pretty well. And this is a big hand slap for data scientists. If I'm using that number to decide when I should stop, or if I'm finicking with some of these parameters up here, that's bad. Because I've got a holdout set, but I'm using information from my holdout set to kind of play with my model, and I can end up overfitting, not realizing I'm overfitting. So it's really important that you don't use this information. It's better if you use this information to play with your model and tweak stuff. But when I start using this, that's a bad practice. It's just nice to know. I can tell you we got 84% accuracy. After 5 epochs, I can let it keep running. So that's our first deep net model. So the 84% accuracy, that means out of the 15 to 20,000 images, it went through and tested, I predict that you're a 1, I predict that you're a 6, and it got 84% right. Random would be 10%, if we just randomly guessed. So we're doing really well compared to random. And what you'll see is no other machine learning technique can beat what this DeepNet can do. So random forest, support vector machine, you name your favorite machine learning method you've heard of or some you haven't tried, it won't be able to beat this approach. And that's why DeepNets have been so interesting. So talking about overfitting, so we can add that dropout. We're just randomly nuking parts of the net. And this one is critical. This one's really important. People call it data augmentation. So what they're doing is they're actually creating new examples of data that did not exist in the training set. And so a silly example would be, we've got 70,000 images of numbers. What if I take one of those images and I rotate it 1 degree? It's a different observation. It's not the same observation. Or for the 8s, what if I start flipping them horizontally? That's a new observation that the net hasn't seen. And so people like to go nuts with data augmentation because it allows your net to generalize really well. And a lot of times it's too expensive for you to get more training data. So if I'm trying to predict, I've got some medical data I need to predict if you have this disease. I only have 10,000 images. They're not going to give me any more. Maybe I paid to get the 10,000 images. So you want to be creative on how are you going to create new observations. And so the lofty goal is every single time you send a microbatch to the GPU, it's something the GPU has never seen, which is totally attainable with this data augmentation. And the nice thing with Keras is they just do it for you on the fly. So I can tell it to scale the pixels, I can normalize, I can do all these different things, rotation. So I'm telling it I want you to randomly rotate the images plus or minus 5 degrees. I didn't have to write any code. It's just built in. It's going to do it on the fly when it's sitting there. And I can also tell it, so here I'm telling it to shift the pixels. So I'm rotating and I shift the pixels 1, 2, 3, up and down. And then I can do horizontal flipping, vertical flipping. Horizontal flipping would be really bad on numbers. Like, yeah, the 0 and the 8, we could do it, but this is going to apply to the whole set, so we're not doing, but for faces, like if I'm doing something on faces, I want to predict your age. Yeah, I'm going to horizontal flip that. I won't do a vertical flip. So this object will then fit on the training set if it's supposed to do some scaling. And then on the fly, it will start doing data augmentation. And what you see, so we really didn't have to change. The only thing we changed on our code is now we call this fit generator, and we're passing in this data gen flow. So what this thing is doing is every time it sends data to the GPU, it's distorting it. And this will produce a better model that generalizes better. So you can see it's going through, it's running validation set.
Question.
Yeah.
So is the basic idea that on the first pass through or the first epic you send it in unaltered and then on subsequent epics you do alterations?
This is not doing that. Everything is altered.
So
What?
The originals never make it in.
No, not in their original format. You can be pretty restrictive. Like if I want the rotation to only be a degree. Something that's popular for people that are really good at deep learning, they'll do a lot of data augmentation, and then for the very final, like let's say we're going head to head, we're fighting, I'm trying to beat you, and at the very end they do some fine tuning with the original unaltered data set, and in some cases they've seen that's helped. There are a dozen of these little hacks and tricks that we won't talk about that people do to get that much more, but data augmentation is kind of a given. So if you're doing stuff with time series or like video, images, most likely you're going to want to do some sort of data augmentation to kind of take you to that next level and prevent overfitting. So this is going through validation accuracy. So this is kind of funny because our validation accuracy is 83%. And the reason it started off so high is because I didn't reinitialize my model. So the weights, those little convolutions that were solved for, we left off where we were, And so don't be confused that we started off with such a good validation score. We actually didn't reinitialize everything. So to be fair, I should have recompiled the model and then kept going. And then you'd see that it was comparable, but maybe a little bit better. And how many epochs are we doing? Oh, it's the same. Oh, this is interesting too. So Kara's added this. So one of the problems with data augmentation, these algorithms don't run on the GPU. So that little like you think they would, right? Like OpenCV, like that should really be cranking on the GPU. But most of these, they don't run on the GPU. And what people have found is you end up starving the GPU. So the GPU is going through and working, and then you say, hold on, wait for my CPU to do these little things with the image. And so what someone in the community did is they wrote a parallel buffer. So all the images would be pre-processed, and they'd be in a queue, so that way the GPU was never starved, and then they baked it in to the Keras library, so I can tell it how many CPU workers I want preparing my images. And the nice thing about this is I can be really aggressive on data augmentation, and the GPU has no idea. The GPU is never starved for data. Does that make sense? Because it's kind of nuts to think about that you're not utilizing your GPUs if you don't do something like that. And so that's a really slick feature that if you had to write that yourself, it'd just be like one more thing you have to do, but it's just built into that library. So we only did 5 epochs there. So now we're going to do a quick color example. Are you guys, is this too technical, not technical enough? Because this is a really advanced topic. If we wanted to kind of digress to just machine learning in general, we could also do that too. But I think it'll be good to end with a color example because most of you guys, if you do decide you want to do machine learning, you probably want to do it on color images because you. So the validation accuracy was 85, and with a lot of these, you'll run it for a lot more. For the sake of time, we're only doing 5 epochs. Ideally, we might do 20, maybe even more. If you do something crazy like 2,000 epochs, you'll see that you start overfitting. So there is kind of a sweet spot there. You're not going to win an award for running this for 3 months. You'll end up doing more damage than good, even with all these fancy augmentations. And
so do you get back like a function that you can pass an image binary to?
Yeah. So this, so if I come down here, I've got this model object, model.predict. So I could just pass in x test 0, and that might bonk. So we're gonna do this real quick. So you would want something to pre-process your image. Oh yeah, I remember why that's bonking. There you go. So I passed this in, it made a prediction, so this told me that that's a 3.
Okay.
And so what you would have in your code is you'd have a little handler where I upload an image to your web app or however you're handling it, and you would format it into that tensor object for that one image, and you'd pass it in the model and get a prediction. So, and I think that just classified it, prob A. Oh, yeah, you don't. I can actually get the probabilities, but it's kind of hacky. Because it's one thing to say, yeah, it's, it was a 3, but you might want to know the probability, because maybe in some cases you want to just turn me like a top 3 list, like we think it's these 3 things, and that's not going to let you do that. But there are ways to get raw probabilities, and then you can rank them. You could say, if it's not a 3, it's an 8. So you might have an application where you need to do that. So that's how you would do that. And the cool thing about this model object, you can save those raw weights, the convolution numbers, to HD5, numpy. Like you can save it to disk, and then you can import it to a completely different library or write your own once you understand the calculations. So if you're putting something on a mobile app, train it on the GPU, spend all this time cranking away, and then once you have those numbers, you can look at porting it to your mobile device.
How do you save your model?
So they have, so right here, Keras is really cool. They've got
Save weights. My digit model.ht5. So I just saved it, and if I load that, I could load that object in virtually any language that has an ht5 reader, and then I could also take that and export it to something I'm more comfortable with, not CSV, something that's very compressed because these are big data objects. So now we're going to talk about color. So not much changes for color.
The key change here is you'll notice that that number is now a 3. So before it was in 1. So we have a tensor object. This has 50,000 images. That's a 3. So I've got 3. So I got a stack of 50,000 color images. But if I look at one color image, it's actually a stack of red, green, blue, grayscale. So if you've done image processing, I know that a color image can be represented as 3 grayscale images. So all that information is packed in this nice tensor object. And we've got 50,000 trained, 10,000 tests. I'm ready to go.
And the funny thing is,
when I deal with images, I think of X, Y, and color, and the default is the opposite. And so I can't do a plot. The plot's going to get really upset. And so Python has this really slick transpose where I can pass in the axes. I can just tell it which axes to flip. So if you have a multi-dimensional array, it's really easy for me to just kind of shuffle it around. So by doing that, that gets in the right format. We can actually look at the image. So that is, these are 32 by 32 pixel images. They're really small. Can you guys tell what that is? It might be easier for the guys in the back to tell than.
Like a toad or something.
Yeah, it's a frog or a toad. So there's 10 different categories we have to predict, and I think frog is one of them. So the main things that changed. For the input shape, we have image channels where that will be 3 now. Before it was 1. Besides that, nothing has really changed. So we're sending a different type of input, but when it comes through the net, this model is actually more complicated because I have 2 max poolings. So I have 2 different layers of features. The other one just had 1 max pooling. Now I've got 2 max poolings. I've got 3 different dropouts. So these models can get a lot more advanced. Ben mentioned something at the beginning where some of these will have 16 or 19 different layers, where you can get a lot of value just with 3. Like this one will get decent value where you might even consider going to production, but if you want to be really good, then you're going to have something that's deeper and maybe has more features. And so this is also different. So with this optimizer, I can give it a string with very popular optimizers, but if I actually want to put my hands in the optimizer and play with it, I can do that too. So I can define, I can load this. So I did up here, I imported this optimizer, and then I can get into all the parameters in there, where the other one, you're just giving it the default. So before we had a default optimizer, we just gave it. Where here, I'm actually defining. So what these terms do is when I'm solving, so when you think of optimization, think of like a salad bowl, and I've got a marble I'm dropping in a salad bowl where I'm going to sample it. Well, if I'm blindfolded and I'm trying to find the bottom of a salad bowl and I touch it, I'm going to have a guess on where to go next. And eventually, even though I'm blindfolded, I'm going to find the bottom by kind of touching around and sampling. But there's different issues with these optimizers not going fast enough, and you want them to adapt. So you maybe want them to be very reckless at the beginning, and then you want them to slow down to kind of fine tune. So some of that stuff is captured in here. If you don't know what you're doing here, I would just go with a default with some of the more popular ones. So you don't have to really dig into that, but that's available to you. So we compiled it. And this is new here. We're dividing by 255. I was confused for a second because that's not a float, but we defined it. So here we've made it a float, and then we divide by 255. So everything is now scaled at a much smaller range. And then we've got the image generator. We are doing a horizontal flip now. So we didn't do a horizontal flip before.
So that frog image is fair game. We're going to flip that. The trucks, in this data set we have like truck, airplane, boat, bird, deer. Well, we've got some weird things in here, but all of those I can flip them. And then we'll run that. Any questions on the main difference was that color, which you saw right here. The tensor object now has color. That's the main difference. If you were importing your own data set, you might have issues getting into the tensor format. You shouldn't really, but if you've played with NumPy, you need to get your data set into this format. So if you're building a model to predict age, or to predict, is this an Apple product or a Microsoft product, whatever you want to predict, you need to get your data into that format. And then you can use these libraries. So now we're going to run this. And not much has changed. You can see this is cranking away. We've got accuracy and loss. The loss are going down. But we don't have, there's no validation output because it doesn't do that until it finishes the epoch. So it's going to go through all 50,000, and then it's going to go through the whole validation and give us that output. Yeah. I love that ETA, even though it's such a minor thing to add. It's like, if you wrote this from scratch, would you add the ETA? Maybe not. Like, maybe you would. But
better than the spinning circle.
Yeah. Yeah.
After a few days of looking at the spinning circle, I think I would.
Yeah. Yeah, so you can see our accuracy is going up and up. And so while that is solving, and you'll notice when you look at some of these other libraries, some of them are pretty awful. So this is an example of that. This is the exact same model to solve the handwritten data set that we started with. This is written in Julia. It's not as nice to read. It has the same information. So I'm telling it, I'm going to have a data layer. My source is going to be my train. My batch size is 64. I'm going to shuffle it. So that's another thing too. When I'm sending micro batches to the GPU, I might actually want to shuffle. My train set I can shuffle all I want, and there's incentives for me to do that. That way, not only are the images never the same, but the micro batch itself is never the same. It's always like you guys are a micro batch, you guys are a micro batch. You guys will never be the same micro batch together again because I'm just kind of randomly throwing micro batches. So, anyone big Julia fans?
I like any language that has a command called add coffee break.
Oh yeah. Yeah. So the benefit with Julia is this language will be the fastest, one of the fastest on the CPU. So if you were training on the CPU, I don't know why you would do that. Because all the languages, they're really similar with their benchmarking because they are sitting on top of CUDA. They're running on when it actually comes down to showtime, they're running on the GPU. So you're not going to get a huge gain on the GPU. But this library with Julia is getting a lot of traction right now, the Mocha library. I think some people think...
I was just curious, in that Python example you had above, is it just using the GPU off of your MacBook there?
No, it's using it. I have a G2 X large instance on Amazon that's using. I think some of our Macs do support the CUDA drivers, but some of them do not.
Yeah, you have to have NVIDIA.
Yeah, you have to have an NVIDIA GPU. But you could do this locally if you do.
Okay, so that IPython notebook's just running off of EC2.
Yeah, I'm supposed to get a new laptop in a few weeks, and I'm hoping it has an NVIDIA GPU. But it's kind of a crapshoot because I guess like some of the other people I've checked with at work, they don't have. My old one had an NVIDIA one, and then that laptop broke. But yeah, so you can run it on Amazon. Just do Spot. It'll be really cheap. Thought I saw a hand go up. So it seemed like at the beginning there was general interest in machine learning, maybe not just deep learning. So one of the topics, you can let that keep running and I can. So with machine learning, when someone actually explains the magic, this is true like 9 out of 10 times, it's really not that impressive. So once someone explains it to you at a 5th grade level, it's kind of common sense and you're not that shocked by what people are doing. So the classic example is with natural language processing. And so with anyone who has a math background or they're a statistician, if I give them an Excel spreadsheet with 3 columns and it has a bunch of numbers in it, like let's say these are continuous numbers. So I've got all these numbers, and then I tell them I've got this column named y. This is x1, x2, and then p. And I've got y, and I want them to build a predictive model. Anyone at the university, they'll be able to, like, who does statistics, they'll know exactly what to do. They're very comfortable with this. They'll do a linear regression or something. But as soon as I change one of these columns to cat, dog, cat, yes, missing value, they have no idea. Like even someone with a PhD in stats, if they're not trained with natural language processing, they're very confused. They don't know what to do. And the solution is actually kind of trivial. So the solution for this is I would say, in the end, the computer needs numbers, and that's kind of a given. The computer always needs numbers, and it doesn't matter if it's like some advanced deep net that's reading sentiment. It always needs a number in the end. So how am I going to get these to numbers? Well, I since these are distinct, and the example I gave is like, let's say these were gender, like male and female. I could assign a number like men are 2 and females 1, but that could be really bad because maybe a 2 is maybe the fact that I assigned a 2 to men could give it more value. I'm saying men are better than women. And so if that's not true, if they're distinct, then I actually want to create new columns. And so this cat, dog, cat, yes would become their own distinct columns. So the cat column would be created, and that would be a 1 where cat was said, it's a 0 everywhere else. And it'd be a 1 where dog was said, it's a 0 everywhere else. So I just took this complicated example that would stump people that haven't seen it before, and now I've got numbers, they know what to do with it. So this is called tokenizing. And then if we just go to Twitter, so if I go to Twitter and I say Wasatch powder hashtag schemo or something, like let's say that's a tweet, and I've got another tweet which is something different. So this can still be intimidating that they have labels. Let's say this is something nice and this is something mean. This is something nice and this is something mean, or good or bad. So even this can be kind of intimidating, like, oh man, I don't even know what I would do with this because there's so much variation. But we do the exact same thing that we did before. This is called bag of words, where we look at all the unique words and we assign a number ID. And this ends up becoming a ridiculous table. Like we're talking like 50,000 columns and however many tweets you have, like 100,000 rows. And we can build a predictive model from that. But the problem with this approach is I need to come up with a better example, but this is always my example. So if I'm trying to predict if I'm saying something mean to you, and I say you have a bad product, you're a jackass. You have a bad product, you're a jackass. Like if I'm saying that, you're gonna figure out that those words they're not very good. But if I have a tweet where I say your product is badass, this approach is going to give you a double negative. It's gonna say, not only did Ben say something mean, he said something really mean. And everyone in the room is gonna like, no, he didn't. He said something really, really nice. And so the bag of words approach, to try to capture that, not only would they make a column for every single word, they'd also make a column for every single pair. And so now instead of 50,000 columns, I now have 800,000 columns. And that might sound like a mess, but these are sparse matrices. Python handles these very well in memory. You can have an 800,000 column data set and build a predictive model. But no matter what, you reach a point where it kind of breaks down, because what if I add a word in between that pairing? You've totally lost the meaning. And so deep learning is very unique with text. We don't have time to go through a real example in detail, but what deep learning actually does is it scans the text. So it actually reads, so if I have something really long that I'm saying, it will actually pick a window of say 100 words, and it will slide that across the text, and it learns. They call it short-term, long-term memory, where it's able to figure out. You said this. You said bad, and you said ass, but then you said a word in the middle. But I still know that that's a good thing. Where this other approach would, if it's not a specific column, it's totally broken. It's not going to capture it. But then again, this will give you 80%, 90% of the value. So most people just use this approach. Any questions about?
Did you mean to run 200 times?
Oh yeah, so this color example, this is a much harder problem to solve because you've got the color. And so since you have the color, you have more convolutions, and the image is slightly bigger, but because the model is more complex, you're going to need that many epochs to start to get the value that you want. Where the other one, the reason MNIST is so popular is it's really fast. We can actually complete. This one's actually not too bad. Like within a few minutes, it'll complete. Or yeah, you can see the epoch is 95 seconds. But if we look at the other epoch, it was probably much faster than that. Any questions on machine learning? Are there problems that people are confused about? Like, I'm really excited to do this, but I have no idea how to connect A to B.
So I'm sorry, I got your latest security answer to this. Skip it. Can you talk about what the differences between machine learning and deep learning?
Yeah, so deep learning is specific to neural nets that have multi-layers with different layers of features. So we gave an example at the beginning where we showed two images, Harry Potter and John Lennon, and you can see they look similar. And the human brain is making an ensemble of features, kind of a soup of features. You see the glasses, you see the hair, and you make a decision. And the deep learner does the same thing. And so deep learning is just an algorithm toolkit for machine learning. Machine learning has so many other things that people use. A lot of times in production, people don't use deep learning because they don't want to commit to the GPU time or the expertise. But deep learning it's really disrupting a lot of stuff. You have a lot of startups that are starting, and that is the only thing that differentiates them. So let's say you're in the market and you sell Nuvi sentiment analysis. You do these Bayesian approaches. You've got some secret sauce. You're selling them that product. I now start a startup, and I'm using deep learning on text, and I'm beating your benchmark, and I steal your contract. So you have all these new startups where that difference in the error is enough for them to create a whole company. So that's why deep learning has a lot of hype right now. And I think I read somewhere Google employs half of the world's deep learning. It's a huge talent grab.
Well, they've got a lot of data to analyze.
Yeah, and they've got a lot of problems over there.
So basically, deep learning is simply a subset of machine learning.
It's a subset of machine learning. It dominates. It depends on the data type. So if you're dealing with text that is, I would say, long text like essays and emails, and if you're dealing with images, any data set where you have to create features. So time series data like stock, audio, video, images, MRIs, all of those data types, they do best in deep learning, and deep learning is disrupting that space. And for those data types, deep learning is beating humans, which I think is very exciting because we see this a lot. You have subject matter experts. So let's say you've spent your entire career researching the differences between gender by looking at someone's face. You've gone to the detail of looking at muscle mass and fat tissue and coming up with very specific measurements, and you have a whole army of PhDs behind you that do that research, and no one knows more than you do in the whole world about doing that. Well, some high school kid that understands how to do deep learning will destroy your benchmarks, which I think is wonderful. Like we're seeing that all the time now, where you have subject matter expertise that's being trumped by people that know how to do deep learning. So, any
about libraries for different languages, I saw that in Erlang it was really popular to do neural networks. Do they do deep learning in Erlang or other languages?
They have them in a lot of different languages. that just reminds me, I was going to show you a JavaScript example. That's fun. The downside you're going to miss out on is if the language is not being used to actively compete on Kaggle, which is where a lot of data scientists go to box. You're missing out on really cool additions and features that won't exist in that library. So you will be able to run MNIST and to do some of these examples, but you're not going to be able to get the most competitive model available. You need to use Caffe, Keras.
Okay.
Like you need to use one of the core libraries if you want best in class. Okay, so this is a deep learning. This is all open source. This was included in the meetup link. So we are running MNIST, and this is all in JavaScript, which is really fun. So this is running locally on my machine. I didn't install anything. I just went to this website, and it's doing deep learning. I can see my loss function going down. This shows me how many images I'm evaluating. It's showing me some other stuff. My loss function, the training accuracy, the validation accuracy. So the validation accuracy is up to 80%. But then there's some really fun things going on down here. So this is a great tutorial where I can actually look at the activations. So this was the input. So the input is 24 by 24 black and white. And I can look at these different kernels. So remember, the kernel creates a whole new image. So I take that little 3 by 3 square and I slide it across the image. It creates a whole new image. So I can see all my different activations in real time while it's going through and checking. And then I can see which ones we're allowed to continue. Remember the activation function. If you're negative, I ignore you. If you're positive, you can continue. I can see what's continuing on, which pixels. And then if we go farther down, so these are getting, so now we're getting into some of the macro features. At the beginning, these are micro features. And at the very bottom, we have our predictions. So I can actually see, and this gets back to that ranking. Like, so yes, you wanted to see a prediction example, and we just said it's a 3. Well, in some cases, I actually want to rank them. So this is, let's find one we got wrong. So this 4s and 9s, you get those wrong a lot. But I can see the green thing. The green shows me the correct solution. If it's not here, we predicted that was a 9, it was a 0. And as this runs, it will get better and better. So it's a really cool demo. It's showing you a lot of stuff that's going on. This is all JavaScript. If you want to do a git clone and adapt this library to do something different, you can do that.